We're going to talk about the law of sines today. My hope is by the end of Friday, we've got law of sines, law of cosines wrapped up. And then on Monday, I hate to do this to you, but Monday we'll have a test over Chapter 5. I would like to put a day in so you don't have to take it on Monday, and put buffer day in on Monday and then take test on Tuesday. But because, scheduling things out for the end of the year, we're not going to have enough time if I do that. Okay, so that's the plan for now. Today, and I'm not going to see you tomorrow, but I'll see you again Wednesday, we are going to talk about law of sines. We get most of it done today, and we'll leave us about 2 or 3 examples to do on Wednesday for the law of sines. We talked about this in geometry, but I think it makes sense to discuss it again. Everything that we've been dealing with so far, the triangles that we've been dealing with so far, what kind of triangles? They're right triangles, okay? So SOHCAHTOA, these relationships of opposite and hypotenuse, adjacent and hypotenuse, and opposite and adjacent, those are only true because of right triangles. And similarity that exists inside right triangles with angle-angle, okay? If I get to a triangle here, this is a non-right triangle, okay? Law of sines is what's going to take over because we cannot directly use SOHCAHTOA because it's not a right triangle. Does that make sense? Okay. So I want to go through the derivation of the law of sines with you. It's a very easy relationship. Okay. Basically what we do is we start at any one of the angles and we're going to draw a segment that intersects the opposite side perpendicularly. Okay, does anybody remember what that segment is called for a triangle? It is the altitude. Okay, every triangle has 3 altitudes. Okay, some of those if it's an acute triangle like this one, all 3 altitudes are going to be on the inside. Okay, if it were an obtuse triangle, not all, but 2 of the altitudes will be on the outside of the triangle and 1 will be on the interior. Okay. Regardless, though, of the acuteness or obtuseness of a triangle, this procedure would be true. Okay. So it's just easier to work with and realize with an acute triangle, and we'll just make the argument then that the same thing happens when it's obtuse. Okay. Thank you. So I'm going to call that H. Okay. When I do that, does that generate 2 right triangles? And if I have 2 right triangles, so we'll talk about this green one here. And let's do this blue one. If I look at those, do those now allow me in the green one maybe to talk about SOHCAHTOA? Can I look at, and I'm just going to focus on angle A, because that is a complete angle out of the entire triangle, correct? The entire red triangle ABC. I don't want to look at C because that's split into parts, right? Okay. So look at angle A. And I'm going to say the relationship between angle A is I can see that sine of A is equal to H over B. Do you guys agree with that? Look at the green triangle. This is the opposite side. That's the hypotenuse. So this would be true. Come over here and look at B in the blue triangle. If I say sine of B, would that be H over A? Does that make sense? Okay. Is that H the same H for both triangles? So it's the same H right there, correct? So let's do this. I just think making the procedure here a little bit easier is to solve both these for H. Multiply both sides by B. Down here I get B sine of A equals H. And multiply both sides down here by A, I get A sine of B is equal to H, right? And again, these H's are the same, correct? So doesn't that mean that and that have to be the same? So I'm going to go B sine of A equals A sine of B. Okay. Now, and you can do this in 2 steps. I'm going to do it in 1 step. I can divide both sides by anything I want to, right? As long as it's the same on both sides, right? So I'm going to divide both sides by the length AB. And when I divide both sides by AB, do those B's cancel out? It leaves me sine of A over A. And when I do it over here, do the A's cancel out? And it leaves me sine of B over B. And that's a clean looking proportion, right? Okay, clean in the fact that it's minimal parts in the numerator and denominator, and we see that the angles, like A, and the side opposite, lowercase a, match up, right? And then the angle B and the side opposite it, lowercase b, they match up. That is the simplest version of your law of sine. Okay? Now, your law of sines is actually what we call an extended ratio, or extended proportion, I guess. Which means that we should be able to incorporate this angle C as well. Now, you guys don't have to write this down, but we should be able to do something like this. There is one of my other altitudes for this triangle. I could have used that one, or I could have used the one from B going to the opposite side. But if I do this, I'm still going to call that H. Now I'm going to look at sine of C is equal to H over B, right? And I could say sine of B is equal to H over C. Go ahead and solve both those for H. I'd get B sine of C is equal to H, and I would get C sine of B is equal to H. But those H's are the same, so those are the same, right? And because those are the same, just like we were doing down here at the bottom, I'm going to divide both sides by BC. And what's going to lead me to, I'm going to skip a step here, but it's going to lead me to the sine of C over C is equal to the sine of B over B. Does that make sense? So I have, in the same triangle, proven 2 things. I have proven that the sine of A over A is equal to sine of B over B, and I've also proven the sine of B over B is equal to sine of C over C. Is the transitive property existing here that allows me to make the jump that sine of A over A is also equal to sine of C over C. So that produces this extended proportion right there, which is the law of sines. Okay? The law of sines is going to allow us to solve triangles that are non-right triangles. Okay? Find missing angle measurements, find missing distances for triangles that are non-right triangles, provided the correct material, the correct parts. Okay? Obviously, what we're going to do is we're going to take 2 of those ratios, and because right now, if I take the first 2, if I take those 2, there are 4 unknowns, capital A, capital B, lowercase a, lowercase b. I need to be able to take that ratio, or sorry, that proportion, and fill in 3 of those 4 unknowns. Does that make sense? Okay. And then that will allow me to solve for a missing angle or a missing side length. Okay. One of the orientations of parts that allows us to do that is this triangle right here. So solve the triangle where angle A is 75, angle B is 60, and segment C is 340. Okay. Now, I do not care, and I never care what my triangle looks like. I always draw that triangle. Okay? Because it doesn't matter. It doesn't matter if A is actually an obtuse angle or B is an obtuse angle, even though I drew it as acute. Does that make sense? If you're a person that says, I need to make things to scale, go ahead and do it. But I'm just doing this to organize my information. Okay? I'm not doing it because I want things to be to scale. Does that make sense? We say A is 75. B is 60. Okay. And C is 340. Okay. We talked about this in geometry. The way we name segments and angles, okay, if you're using capital letters to name angles, and then the lowercase version of that letter should be the opposite side. Okay, so that's where I knew to put lowercase c in this situation. Okay, if we go off of orientation of parts that we learned in geometry, this is an angle and an angle, and in between those, sandwiched in between, let's call it the included side, is a side. You guys remember saying angle, side, angle? Okay. Now there's a lot of different, we talked about congruencies with angle, side angles. We talked about similarities. We talked about potentially even inequalities. Okay. But angle, side angle right now is the orientation of parts that we are able to use the law of sines to find missing parts. Okay. Now, if I'm going to use my proportion, okay, the sine of an angle over its opposite side equals the sine of another angle over its opposite side. What I like to do is I like to fill in kind of a static proportion. Okay, I know the signs are going to be in the numerators. Okay, I just got to figure out what goes in the parentheses and then what goes in the denominators. Okay, and I'm always keeping in the back of my mind that in order to solve the proportion, I can have how many variables in there? You can only have one. Okay, so I'm going to call this side here lowercase a, this side lowercase b. What were the things right here? What do those represent? What are they? Are they angles or are they distances? They're distances. I can't have two unknowns down here, right? So because I can't put A and B down there at the same time, the same proportion, what does one of those values have to be? One of them has to be 340. Which if one of them has to be 340, then I better know what angle C is. What is angle C in this situation? 45. It's a triangle angle sum theorem, right? Okay. They give you two angles, you automatically know the third one through subtraction. So now that leaves the door open for me to decide, okay, because now I got to use either 60 degrees or 75 degrees. I'm going to use 60 right now. So put 60 there. So what should go opposite 60 is lowercase b. Does that make sense, everybody? When you do these, and I like to draw that picture, is I will circle either the segments and the angle. I might circle both, whatever, doesn't matter. But I connect them with segments in, and I get that X every single time. Okay? And we'll do this again with segment A. But you cross your parts, relate your parts as opposite. Those will be the four things that always go in your proportion. And of those four things, one of them needs to be variable. Okay? So if I look at doing this exact same thing for B, I'm going to, or not B, sorry, A. I'm going to take, again, this was 45. I have to use that one. Sine of 45 over 340 is equal then to, okay, trying to solve for A. Now it's going to be sine of 75 over A. If I look at the things, those two things are related, and they are found in that first ratio. And then these two things are related, and they're found in that second ratio, right? And we see that cross, or that X in between in our image. And that X right there basically tells me, this will be every single time we use the law of sines, it tells me those are the four parts to use. And if you're going to be able to do and use the law of sines, that means all four of those parts, three of them should be known. One of them will be unknown. Is that okay? All right. That's the way I always set these up, and we'll talk about this here in a moment as well. But I always set them all up before I start doing algebra, because we're going to set this one up and solve for B right away, right? And that's fine. You can do that. and then set this one up to solve for A. I like to set them up all at once, or as much as I can at once, because it's going to limit my ability to use rounded values. And I want to limit how many rounded values I use. Does that make sense? Okay, if I can avoid all rounded values, I'm going to. I want to solve for A first. Okay, it doesn't matter, but there's going to be a reason for doing it this way first, at least as instruction. So proportion 3 cross multiply. So you get A sine of 45 is equal to 340 sine of 75. Now sine of 45 it's just a coefficient. Okay, if we're typing our calculator, it gives like 0.707 back. Okay, so what would you divide both sides by here to get A isolated? Sine of 45. You're going to cancel, come over here, sine of 45. So A is equal to 340 times sine of 75 divided by sine of 45. Okay? Now, I've isolated A. All the numbers on the right-hand side, 340, 45, and 75. None of those were rounded, right? If I were to ask you what is the exact value for A, that is it. But if I were to give you a pen and a number line and say, go put that on the number line, would anybody know where that's at? No. Okay? But if I wanted to use that number later on in another calculation, it's probably best to use it as that version right there than its rounded version. Okay? So, and we'll get to that later on in other parts of the course. Let's take Desmos, 340 sine of 75 divided by sine of 45. And this might be one of the first times we've actually seen here that we type everything in, and now the answer, I know I should be getting a distance, right? And this answer actually tells me something about, I've done everything correct, but it tells me something about my calculator. It's in radians, because that answer doesn't make sense for a distance, right? So that should elicit, maybe I need to check my mode, change it to degrees, and there we get the distance for that segment A, 464.45. Okay, or approximately that. The reason I say the reason I set up these two proportions first and then solve for A and B is because if I would have done this, I would have solved for A first, that would have opened the door for me in this proportion right here, solving for B. Instead of writing a sine of 45 over 340, I could now say sine of 75 over 46 or 464.45. Does that make sense? Okay. I could use that, but that 464.45 is what kind of number? It's rounded. So will that really give me what B is, or the best answer for B? No. So if I can avoid using rounded values, I'm going to. When you get into WebAssign, it shouldn't be a huge deal. If you want to use this rounded value to find other variables, it's not a huge deal as long as you are very conservative with your rounding. Okay? If they want this to be like to 2 decimal places, I'm going to use a rounded value as an intermediate value in here. I would maybe round this to 4 or 5 decimal places. Does that make sense? And then my hundredths would not be impacted here with B. Go ahead and solve for B. There's 2 ways that we can solve for B in this situation. Okay? I'm going to cross multiply just like we did over here. B sine of 45 equals 340 sine of 60. B equals 340 sine of 60 over sine of 45. Is that okay with everybody? Same exact algebra, right? Okay, all these problems are going to incorporate the same algebra, same steps. So now this would be 60. That's the only thing that changed there. And I get 416.41, right? 416.41. Okay. But I'm going to do this one a little bit differently. Because that's a unique number, isn't it, for a triangle? Is 45 also one of those unique numbers for a triangle? If you remember back to, I think it was section 5.2, and if you're not remembering this stuff right now, it will be ingrained in your brain once we get through chapter 6, or at least through like the first 2 sections of chapter 6. But does anybody know off the top of their head what sine of 60 really is as an exact value? As a radian, it's pi over 3. But what is the opposite side divided by the hypotenuse of every 60-degree angle? Okay, so you get, so across from 60 is your n radical 3 side, right? But if it's sine, it's over 2n, isn't it? So doesn't that sine of 60 turn into radical 3 over 2? So I've actually got 340 times radical 3 over 2. That's what sine of 60 is. And if we go to a 45, 45, 90 triangle, the sine of 45 is radical 2, because you got your n and your n as your sides, and then n radical 2 is your hypotenuse, right? So I'll have n divided by n radical 2 reduces to this, okay? Now, lots of different ways you can approach this. You want to multiply the numerator out first? You can. I like to do this. I like to look at this as being 340 over 1 times radical 3 over 2 divided by radical 2 over 2. Why would I like to do it that way? What's that telling me about this fraction right here? How can I reduce that then? It's going to be, because the denominators here are both 2, right? So it's going to change to 340 over 1 times radical 3 over radical 2. Does that make sense to everybody? Okay. And that's just a shortcut to that process of taking that fraction and multiplying by its reciprocal to the top fraction. Okay. When they're the same, those are just going to cancel, and you're just going to leave me that over that. So do I like radicals in the bottom? What would I multiply by? So up top, that's going to give me 340 radical 6. On the bottom, it's going to leave me 2. Is that 170 radical 6? Go to Desmos real quick, and let's see the comparison here. 170 square root of 6. Is it the same value as 340 sine of 60 over sine of 45? Okay. But here's the thing. You got to pay attention. Web assign might say, type it to the hundredths place and put your answer in the hundredths place. Tests will do this. Quizzes will do this. Okay. Handwritten stuff. Okay. The final for the class written by Rhodes will do this. Okay. If they ask for a hundredths place, that's fine. Go ahead and put it in a decimal, however you want to do it, to get to a decimal. Okay. If it asks for an exact value, and they'll say exact value with simplified radicals, they're wanting the 170 over radical 6, right? Because if I type in this, I mean, we were going to talk about this logically, that is the exact value. But when it adds the fact that says exact value with simplified radicals, that means don't use that form, use that form. That kind of make sense? What I love about geometry and trigonometry, but trigonometry mainly, is that, yeah, we're going to learn these facts about law of sines and all that kind of stuff, and all these neat relationships between angles and side lengths and that sort of stuff. But I think the greatest byproduct of trig is that it refines your algebra skills. And why is that essential? A lot of you plan on taking calculus. Am I correct with that? Okay. Do you know what's hard about calculus? Nothing but the algebra. Okay. You already know everything you need to know for calculus. Calculus is slopes and areas, and you already know all you need to know about slope and area. What's hard is the algebra that is in there. But if we can refine those skills with the algebra as a byproduct of trig, it's going to make that class a little bit easier for us. Okay. Is that something we can do? Okay, so that's the law of sines. That was the angle side angle orientation. Okay. Come down here. It's a different orientation in example 2. Example 2 uses, if I look at this side right here, And we kind of view this a couple different ways, but I'm going off of what is explicitly given, okay? Because we know what angle B is, right? Okay? But I'm going off of what is explicitly given here. This would be angle, side. Does that make sense? You're given two angles and a side that is not between them. Okay? Now, because of the triangle angle sum theorem, we know that this will be 135. So that could convert over then to angle, side, angle. Does that make sense? Okay? Much like the other one, started as angle, side, angle, but because we knew two angles, we could kind of come up with a third one, so it could give me angle, side if I wanted it. Does that make sense? So angle, side, and angle, side, angle are two of the orientations of parts that you're going to use for the law of sine. Okay? If I'm going to solve for missing parts here, okay, we've got angle B already figured out. Let's say we want to solve for A. Okay, so I'm going to set up my ratio, my static ratio, where I just plug in those things there. If I want to solve for A is going to be my variable, right? So what is opposite A? 20. So 20 needs to go in that ratio. Okay. If I use 135 here, what's the problem with using 135? Yeah, I've got a B there, and I've got two variables. But there's nothing wrong with this, because if we want the extended proportion, remember, we could say now sine of C over the opposite side of C, and you get 80.4, right? If you want to do it that way, every single problem, you should be able to do that. You should be able to take the sine of an angle, put it over the side opposite, equals the sine of the second angle over the side opposite it, equals the sine of the third angle over the side opposite it. And now you just got to decide, okay, which two ratios do I take so that I only have one variable? Does it make sense that you're going to take that one and that one? So that gives you sine of 20 over A equals sine of 25 over 80.4. Does it make sense that you could also have taken that one and that one? So you get sine of 135 over B equals sine of 25 over 80.4. I actually like doing it that way, for the mere fact that I know that I'm never going, if I write all three of those down, I'm never going to accidentally use the wrong angle compared to the wrong side, or and at the same time, it then guarantees that I can set these up to where I don't use any rounded values. Is that something we can do? Do we need to solve that one any further for A or B? You guys can do that on your own. Okay. Make sure it's not a huge deal at the moment. Make sure that when you're using your TI 8384, because we're only dividing by one quantity right now, it's not a big deal with your parentheses, but eventually parentheses are going to matter when we start talking about law of cosine, so just be careful with it. That's why I like to use Desmos, because obviously it writes it like I would have written it by hand. Just be cautious. Okay. So that's an angle side, and angle, side, angle. And all these questions so far have asked us just to deal with finding distances. We will see some examples on Wednesday that ask us to find angle measurements. But it's the same relationship, except for now we're going to try to solve for a missing angle instead of a missing side. Okay. But that gets us today. I just want to talk about, introduce this, the ambiguous case. Do you guys know what the word ambiguous means? We talked about this in geometry. I actually pulled off the applet that I'm going to show you came from our geometry. I created it when you guys were geometry students. So we've talked about this. Okay. Anybody remember what ambiguous means? Unclear. That's a very good way of stating it. Okay. A lot of dictionaries will say that it's ambiguous means left open to interpretation. Okay, which is analogous to saying unclear, right? Okay. If I say I have a friend named Pat, it is unclear or is left open to interpretation until you have more information about this person, whether they are a male or a female, correct? Okay. So that's the ambiguous case. We could, and we see here it says you could have no or none, one or two different triangles provided the information given. Okay. What's going to happen here, if you guys remember back to geometry, we had some orientations of parts that guaranteed congruency. Side, 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 guaranteed congruency. Side, angle, side, guaranteed congruency. And I'm talking about congruency because what happened, the reason I can use like angle, side, angle in that last problem, or the first problem, the reason I can use that the way that I did is because based on that information, the way this is provided right here, angle, side, angle, with that data, there is one and only one triangle that can be created that would be congruent to this one using that same information. Does that make sense? I can't create a second triangle using this exact same information. That would not be this triangle. Okay? That's what congruency means. Okay? Take these parts, define what these parts are, how big they are, and you can, and every one of us have those parts in front of us. Every one of us is going to make the exact same triangle. Does that make sense? Okay? Same thing happens with angle, angle, side. Those guarantee congruence. You guys remember the one that does not guarantee congruence? ASS. Okay. Now, for obvious reasons, we call it side-side angle, right? Okay. But I want to write it this way. Because the ambiguous case is a pain in the butt. Okay? And if you can remember that, if you can remember the parts that they just get, because it's not going to tell you. Okay? You're going to go through, you're going to give you 10 questions. Some are going to be angle, side, angle, some side, angle, side, some side, 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 some angle, angle, side, some angle, side, side. And it's not going to tell you, hey, this is the ambiguous case, remember here. Okay? Because it's going to train you angle, side, angle, 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 side. It's going to give you like 3 or 4 that you do just the law of sines the way we did the last 2. And then this one's going to pop up. And what are you going to do initially? You're going to think it's just like the other ones, right? And you're going to get an answer and type it in, and you're going to be wrong because there might not have been an answer, or there might have been an extra answer. Does that make sense? Okay. So you always got to look at the parts. And I'm always looking to see if angle, side, side is what they give me. I don't really care if they give me angle, side, angle, or angle, angle, side. I don't really write those down or think about them that way. I'm just always on the lookout for angle, side, side because it's the different one. And if I see that one, I know I got to treat it differently. If I don't see it, then I just go on about my business. Okay. But you treat angle, side, side differently. Okay, because it does not guarantee those parts in that order. If I gave you all a, let's say a 45-degree angle, like a 6.5 inch segment, and let's just say a 6-inch segment. If I gave all of you those 3 parts and said, everybody create a triangle on your desk, there's going to be 2 triangles that are created. They're not all going to be the same, okay? Because congruency is not guaranteed. And that's what this is getting at, okay? So that's something we've got to look out for. And I've got a demonstration of this here, okay? So what I'm going to do right now, I'm going to set this up to where we have a 45-degree angle. So the image here, actually, let's see here. I want to make sure I'm zoomed out to the same. All right. So triangle on the left, triangle on the right. They're the same triangle, yes? Okay. Right now, this angle right here, it's not showing up for whatever reason, but that's the 45-degree angle that you're seeing over here. Okay. So what I've given you here is I've said, here's a 45-degree angle. Let's say maybe I cut it out of cardboard, and I hand you a 45-degree angle out of cardboard, okay? And then I give you a 6.5 whatever unit segment of yarn. okay? And then an 8.8 segment of yarn, okay, or string or whatever it may be. And I tell you, configure them to create a triangle using them in the order of angle side, side. So you have to start with a 45-degree angle, right? Okay? At that vertex, that 45-degree angle, you take your 6.5 or your 8.8, doesn't really matter. But you take your 6.5 and you align it so it follows that edge of your angle, correct? And it terminates right there. Now you're going to attach right there your 8.8. Okay? And this 8.8 is free to rotate everywhere, right? Okay? So this was defined by that side of the angle. Let's say maybe I put a nail right there in that piece of yarn. This one can rotate, but it needs to rotate to where it would intersect that line right there. That is the extension of the second side of your cardboard 45-degree angle, right? Does that make sense? So then I'm going to rotate this down to about right there, and I'm going to create then that triangle. Does that make sense? Okay. Now, here is the idea. Can I rotate that any further? So let's say student 1 created this on their desk. Student 2 creates this on their desk. Can student 2 create anything else other than that triangle? That's the only thing that they can create, right? So with those parts, angle side, side, with those parts, we can create one triangle. Does that make sense? Okay. Let's go a little bit more drastic. Let's say that I give you this 8.8, and let's say we cut that down to being less than 6.5. I give those parts to everybody. No matter how I rotate that, will that ever touch that predefined third side right here? Because it's got to intersect to create that distance to that third side, right? So does that make sense that with that distance, there's no triangles that can be created, right? Okay, so there's some ambiguity there. Based on just these lengths, I could have right now no triangles or one triangle, but let's do this. Let's make this segment 6. Come over here and make it 6. Come on. So if I put these segments in front of you, student A, I want to zoom in here, try to get the best intersection there. Student A might be able to make that triangle right there, correct? Okay. Their neighbor might make the exact same triangle. Their neighbor might go there. But could their neighbor do that? We'll zoom in here pretty far to get the best here. Can we see that triangle there? So student A gets that triangle. Student B gets that triangle. Would you agree that the lengths or the distances, that third distance, would be different? Okay, so here's a situation where two triangles do exist, but they're completely different. But look at the angles that are, we know they both have a 45-degree angle. Beta is 45 in both these. This one here turned out to be 50. This one turned out to be 130, right? What's the relationship between 50 and 130? They're supplementary, okay? So on Wednesday, when we talk about the way that we distinguish whether we have one solution or two solutions, once we know we have a finite number of solutions, once we realize that there are none solutions, doesn't really make a whole lot of sense saying it that way, but once we realize we have either one or two solutions, the way we distinguish whether we have two overall is that idea right there. It's based on the idea that these would be supplementary. Okay? Does that make sense? Here, if that's 130, that's 45, that gives me enough to have that angle right there, correct? Okay, I haven't exceeded 180 in that triangle. Here I've got 50 and 45. It gives me room for that angle up there. Okay. So that's the relationship that we are going to look at and use when angle side is presented to us. Okay, and we'll do some examples. Start class on Wednesday with examples of that. Well, I think I've got an example that asks you to find an angle measurement as well. Actually, this will the initial part here, the initial component that you have to find with angle side is an angle. We'll have to find what this angle right here is. So we'll use the sine inverse command to do that in that problem. I'm going to open up a WebAssign here in a little bit. It is not going to be due for a while. I'll probably actually make it due at the end of the week. Okay. Like I said, though, by Friday, I want to be done with laws of cosines. Now, the law of cosines assignment, I will probably push that back beyond the time that we take a test. So if tests are going to be on Monday, the law of cosines assignment probably won't be due until like Tuesday or Wednesday. But just to give you time to maybe push the assignment aside and study for the test. But that's the plan as we move forward. Because of all the cancellations we've had, I know we've done the e-learning days in lieu of cancellations or being here, but we really didn't get through any new content, right? Like it wasn't like we're in class and getting things done like we can in class. Because of that, we're a little bit behind schedule. Okay, so we're going to try to make up that time as we move forward. But once we get through chapter 6, we'll go through slow. Chapter 7 we'll go through slow, and then 8 and 9 will be quick. Okay.